We're going to talk about a whole selection of different ways to solve recurrence equations. You're going to add them to your set of tools, and you'll be able to solve pretty much anything that'll come up in most computer science applications. Recurrence equations come up most often in algorithms, and they come up most often in particular kinds of algorithms where you split the problem into 2 halves or 3/3, where you divide it, not where you break it up into n and n minus 1 and 1, or n minus 2 and 2. That's usually a bad way to break up a problem. The best way is to divide it. That makes the algorithms generally faster. And those kind of algorithms, which are recursive algorithms that split a problem into 2 different fractions, those are called divide and conquer algorithms. There's a whole 2 or 3 weeks we'll talk about this in algorithms. And we'll talk about how to solve these recurrence equations. So when I get up to it in algorithms, I'll say, hey, remember how to do this? You'll say no, but I'll be able to review it in 5 times the speed as if you'd never seen it before. So that's the idea. You're going to see it now first. All right, questions so far? All right, so let me give you the big picture. I'm going to write down all the different methods that I'm going to go through with you to solve recurrence equations in the order that we're going to do them and the order that we have done them. So these are methods for solving recurrence equations. In doing this today, we're going to come up with a lot of algebra. Don't get too bogged down in the algebra. If you lose track of the algebra, don't lose track of the technique that's behind it. Methods for solving recurrence equations. 1, the one that I call repeated substitution. And you've got to be good at adding sums and knowing what sums add up to. Call this the master theorem. It's kind of developed that name over the last few years because people have called it that in a book. The first time I ever saw this theorem, it wasn't called the master theorem, and I'm not sure anybody really knows who created this. I think it just kind of grew with lots of different people contributing to it. I'll tell you what this means, but this is basically somebody went ahead, picked a whole class of recurrence equations, did repeated substitution, and wrote down and proved what the general complexity of the answer was based on things that you could look at before you bothered even doing the substitution. So it's a shortcut for bothering to do all the sums. And it takes care of a whole class of problems that you normally would have to do with method 1. And I'll talk about that later. So this is usually used for the class of algorithms called divide and conquer. This is the one that you see most in computer science. That's why they call it the master theorem in algorithms. Next method. A change of variables. Sometimes when you change the variables of a recurrence equation, you take something that looked ugly at first, and then it's something that's a lot easier to work with. You can solve the second thing that you came up with, and then convert it back to a solution in the original thing by reversing the change of variables. And I'll show you a couple examples of that. 4. Guess the answer, and prove by induction. I'm going to check the ones that concentrate primarily not on the perfect closed form for the answer, but on the overall complexity. The master theorem and guessing the answer and proving it by induction is guessing the overall complexity and proving it by induction. So I have a recurrence equation. I don't have the slightest idea what it would sum up to, but I have a good feeling that it's a linear time recurrence equation. I think it's order n. So I go ahead and guess that, and I can prove it's true by induction, even though I don't have to actually calculate the sum. So that's a very nice, powerful technique. There's 2 more. There's a whole class of recurrence equations that don't come up that much in computer science, come up less frequently than the divide and conquer, but do come up nevertheless. And they are a class that is completely well understood and has a mathematical theory, just like differential equations has a mathematical theory. And we'll go through this. This will be the standard kind of calculus stuff where you just learn mechanics and you do a few examples and you repeat them. This is relatively easy from a math point of view. You don't have to discover much. You learn the technique, you repeat it. And it's called linear homogeneous equations. How do you spell homogeneous? Close enough. Homogeneous. All right. All right, linear homogeneous equations. And then finally, as if you thought you'd never see it again, you can solve recurrence equations by doing diagonalization. Okay, so you all are going to have to go back and remember how to do that, and I'll do one example of this here in class. We're actually going to solve the Fibonacci recurrence equation using linear algebra like you did last semester, 2 semesters ago. All right, so here are the methods. We've done this one. Check. We're going to do this one right now, and if I have time today, I'm going to go through these two because the ideas there are easy. And then on Monday, I'm going to try to finish these two. And then Tuesday, I can move on to some different things. That's my goal. Worst case is we get through the end of this Tuesday. Okay, that's our big picture for the next couple of days. You'll get all of the intuition behind the proof that you ever wanted through these two examples. So in some sense, it'll be proof by example, which is no proof at all. But if the example's general enough, it really is a proof. So here are the 2 examples that we'll start with. Well, actually, make it 3. Here's one. Here's 2. These are divide and conquer algorithms that turned up with these recurrence equations. You can tell they're divide and conquer because the smaller case is a fraction of what you started with rather than something subtracted from it, because it's divide by 2. Divide by 2. It could be divide by 3 or divide by 10. There's a lot of other things it could be, but in these cases it's divide by 2. The numbers in front here for divide and conquer algorithms need to be constants, not n's. Otherwise, it's just too many subproblems. So you'd like to keep this to 2 and 3. And then there's this combining factor, which is the amount of time it takes to take your subproblems and combine them together. So if you're doing recursion, these represent the recursive calls. And this represents the amount of work your algorithm does in between recursive calls, or before or after the recursive call. Keep in mind, every recursive algorithm you write has a recurrence equation associated with it that says how much time it takes. Every recursive algorithm you write has a proof by mathematical induction that it actually does what it's supposed to do. You assume that the smaller case does what it's supposed to do, and your connecting code makes sure the bigger case does what it's supposed to do. So induction is the proof on any recursive algorithm. Recurrence equation is the time complexity in any recursive algorithm. They all go together. And these are all divide and conquer algorithms.
What's the situation if n is not even? You're confining yourself to 2 to the k?
Yes, for the purposes of doing the computation, we'll confine ourselves to powers of 2, but it won't actually affect the overall complexity. We could just put floors and ceilings, and it will just look messier. But let's assume that our size of our thing is always 2 to the k, so we can just go ahead and do n over 2, n over 4, and never worry about fractions. It's a good question. All right. This comes from a real-life algorithm. Actually, so does that, but this one's very well known. This comes from an algorithm sometimes called merge sort. In merge sort, you're going to sort a whole bunch of elements. Okay? And here's how I do it. I split them in half. I give half to Teresa, and I say, go sort this for me, please. And I give half to Tony. I say, go sort this for me, please. They each sort it. They come back to me. And now I have 2 sorted lists, each half the size. And what do I do with them? I merge. I give them to Michael, and I say, Michael, merge these for me. And he takes these 2 sorted lists and he merges them, which is a much faster process than sorting. Because merging, it's kind of just like there. You compare, you keep a pointer at the top, and whichever one's bigger goes interleaving the cards as you go. It's proportional to the time that it takes to run through both lists. It takes linear time to merge. So this is the merging step. And here are the 2 recursive calls, each half the size. This comes from merge sort. There's lots of algorithms that have the same recurrence equation. Here's another one with the same recurrence equation. We'll call this I made it up on the spot sort. All right? We take a list of numbers. We want to sort it. So I find the median. That's the number that's the middle number, not the average, the middle number. I take all the numbers that are bigger than that, and I give them to Peter, and I say, sort these for me. I take all the numbers that are equal or smaller than that, and I give them to Neil, and I say, sort these for me. And they come back with sorted lists, and what do I do with them? I just stick them together, and I'm done. So where's the work? Still two problems. Each one is half the size. Still this is the same. But where does this n come from?
Finding the median.
Right, finding the median. It's the work that I have to do at the beginning to find that middle spot, to find that center element. And it's not obvious at all how to do that in linear time, but you can do it in linear time. A real clever algorithm does it in linear time. So that's another algorithm that has the same recurrence equation. We're going to solve this, see what it equals. You should still know how to do what we're about to do, but it would help to be able to short circuit it if you can. We're going to do the same thing here. I'm not going to talk about algorithms anymore, but this comes from a problem where you can split it into halves, but you have to give it to 3 different people. It's a little bit like that Towers of Hanoi that doesn't work problem, right? Split it into half, do 3 separate half Towers of Hanoi, and then do a little work connecting them. Okay, let's do this one first. The technique, again, is to get rid of these capital T's. I'm going to do this just enough to get a pattern, and then we're going to write down what our pattern is. So 2tn over 2 is 2tn over 4 plus n over 2. That's using this equation again in order to get a value for tn over 2. And now we're going to take that value and substitute it in place of tn over 2 and get a new equation for t of n. It's going to be 2 times all of this. So it's 2 squared tn over 4 plus n plus 2n divided by 2. That's our pattern. Okay so far? If I do it many, many times, who thinks they can see the pattern already? Anybody see the pattern already? I know Sam sees the pattern already, even though he's not telling me. Who else sees the pattern? Who thinks they know it? Chris, do you know it?
2 to the r.
If you do it r times, this becomes 2 to the r, t
N
over 2 to the r. And then what does the sum look like?
Well,
Let's try to leave in all the details we can.
okay.
So n plus 2n over 2 plus, how far does it go? What happens next? Am I messing you up?
No, I just
2 squared n over 2 or 2 squared n over 2 squared? Let's do it, maybe. It is. Tony, you're way ahead of me. Right. If you do this twice, you got 2 n's. If you do it 3 times, you're going to have 3 n's. So, dot, dot, dot. Let's actually rewrite this easy. 2 to the r, n over 2 to the r plus r times n. And we'd like to make this t disappear. How do we make this t disappear? We need n divided by 2 to the r to be equal to 1. That means n equals 2 to the r, and r equals log base 2 of n. There's a convention that if I mean base 2, I'm just going to write lg. It saves me from writing the little 2 underneath all the time. So r equals log base 2 of n. Let's put it in. This becomes 1. T of 1 is 1. 2 to the log base 2 of n is n. So when r equals log of n, I get n plus n log n. And that's big theta of what? Big theta n log n, because the n part is smaller than the n log n part. You should know that theorem that if you have the sum of a lot of different functions, then the big theta of the whole sum is big theta of the biggest one. You can prove that theorem, and you probably know it intuitively already. Just reminding you. So this is big theta n log n, and that's no surprise because, as you know, sorting algorithms that are good generally take n log n. That's the best you can really do.
Oh, you just said that you only have to look at your base term when you have a series.
Oh. If you have a sum, I should say a finite, well,
Okay.
you're talking about this. Or this. And you're saying this is big theta n squared, and this is big theta n cubed. And, well, good point. I wasn't talking about things like this. I was talking about things that look like this. Where you can just, because here these things are not in terms of n, so there's an implication here that there's something else going on. But good, right. Okay, questions about this n log n example. Try to imagine that there was an n squared here also, because that's the third example I want to do, so that when we get to that third example, we don't have to go through the whole thing from scratch, but we can change the appropriate places more quickly. We're going to do one example here with n, then we're going to do an example here with n squared. Okay. Here's the first step as before. Tn over 2. Here, let me get some help. What's Tn over 2 going to be? We're going to substitute in for this, so we need to know what Tn over 2 is. 3Tn over 4 plus n over 2. Every place you see an n, you put in your n over 2. And now we're going to take this value and put it back into here. So Anthony, it's good to see you here instead of watching me virtually. Tell me what I get here.
3 squared.
Good.
Tn over 4 plus n over 2. Oh, wait. Yeah? No?
I'm waiting.
Plus 3n plus...
This n over 2 also gets multiplied by that 3.
Oh, right.
So you get n over 2 plus
3n over
n plus 3n over 2. Good. What happens if I did it again? What would happen? Three cubed t n over 2 cubed plus n plus 3n over 2 plus 3 over 2 squared n. This new term comes from the fact that we multiplied these old terms by 3 over 2. So this became 3n over 2. This became 3 over 2 squared n. And then we had the original n from our equation. The next time, it would multiply each of these again by 3 over 2. So let's write down our general result here in terms of r. T over n is 3 to the r Tn divided by 2 to the r plus n. And I'm going to factor out the n because it appears in every place exactly once. Let's write down what we get. 1 plus 3 halves plus 3 halves squared all the way up to, what's the last term? This exponent here is 1 less than the exponent there. So we go all the way up to 3 halves to the r minus 1. Good. That's an r. All right, so you geometric series experts should be able to add this up. It goes up to the next exponent, 3 halves to the r, and you divide by the difference between
Minus 1.
between 1 and 3 halves. The difference between 1 and 3 halves is a half. You divide by a half. That's multiplying by 2. So this whole part here is 2 times 3 halves to the r
Minus 1.
minus. this then, right? Minus 1, right? If you're not sure where this turned into this, we've done it a few times, and you can go back and review it separately. Make a note to yourself. Review geometric series. The trick is to call this x, multiply both sides by 3/2, do a subtraction, solve for x, and you'll get this. You could all do it, I know, if you had the time and focused on it. Most. Right. So here again, we want r to be equal to log n. Same thing as before, because we want this to turn into t of 1, and you want the t of 1 to disappear. So you get r is log n, 3 to the log n plus n times 2 to the 3/2 log n minus 1.
We just assume the logs are all in base 2, or you don't.
Yeah, LG means base 2, but they are all in base 2, definitely. They're definitely in base 2. And they're all relative to each other, a constant, so it probably won't matter. Something I mentioned yesterday, I'm going to prove it right now in a couple seconds and remind you that you learned it before a couple months ago. This is a good thing to know, that if you have a number raised to the log 2 to some other number, that you can basically swap these two and it's identical. So how do I convince you this is true? I'm going to resort to something else that I think you will remember. You probably all remember this because I made a big deal about it. What is log base a of b times log base b of c? Anybody remember that identity? Log base a of c. The b's in some ways cancel.
It's an A.
That's an a. Good. You can prove this with the rules of logarithms, or you can just remember it. But this is going to immediately imply that this is true. And there's a lot of ways to see it. This is one way. Let's look at these equations and take the log base 3 of both sides. The reason we're going to do that is because log base 3 of 3 to the something equals just the exponent. So take the log base 3 of this left side. What do you get? Log base 2 of n. Taking the log base 3 of both sides. The log base 3 here is log base 3 of n to the log base 2 of 3. Question mark, question mark. The log of something raised to a power is the log base 2 of 3 times log base 3 of n. Okay, I just brought the exponent out in front.
And the 3's cancel.
Log 2, 3, log 3n equals log 2n. Yes, that's true. And the 3's cancel, yes, in a way. So the fact that these two are equal depends completely on the fact that this equation is true. And this equation is true because you all remember that from 2 months ago. Whatever you remember is true. Get used to the fact that when you see stuff like this, you can switch the numbers. I'm completely serious because you want to think of it notation-wise. Notation helps a lot. The fact that you can switch these numbers is going to make your manipulation fast. Don't go into the tank and rediscover this every single time you use this. Make sure that if you have to convince yourself it's true, you can. But once you do, turn that into a black box, turn the neurons off as far as why it works, and just start thinking about this mechanically. Get it to be automatic, because then you'll recognize patterns. So now we're going to go back to here and try to put our automatic gears in gear and use this information. Let's see. 3 to the log base 2n becomes what? N to the log 3. Well, that's something that looks reasonable. N to some number. You can do log base 2 of 3 on your calculators. You can figure out what it is. Plus 2n times, what is this going to be? N to the log 3/2.
If you're just looking for large O, you could now drop the -1.
What about these two? Which one is going to be bigger?
They're the same.
The 2n.
They're the same.
They're the same? Let's check.
No, because the log.
And the log up there is LG, not LG.
LG, right. Well, we'll check it in a minute, but before we check it, I want you to notice the following thing that happens when you do these problems. You always get two pieces in your final answer. You get the piece that came from this part, and you get the piece that came from this part. This is the part that winds up your recursions, that keeps track of the structure, and this is the part of all the work that it takes to glue those pieces back together. Sometimes the gluing is the dominant factor. I do a lot of work when all my friends come back and give me the answers, and if I include all the gluing that their friends did when they got their answers, it all adds up to this. And sometimes the gluing is trivial and nobody does anything except just pass results back, and then the actual construction of the tree and how many people are actually involved becomes the dominant factor. This is the number of people and the number of recursive calls and the structure of it. This is the gluing that gets done at each step. The master theorem is a way of deciding which one of these is dominant, if either one, and then quickly deciding what the big theta should be. We're doing it by substitution here. We haven't hit the master theorem yet, but we'll hit it soon. We're going to compare these two in this case and see which one is bigger. So this is n to the log 3, and let's simplify this a little bit. Sam's right, we don't need the minus 1. That's noise in the big theta picture. This is 2 to the n times n to the log 3 halves. So it's 2 to the n log 3 over 2 plus 1.
Is the same as log 2 of 2.
Okay.
Add log over multiplying.
Log 3 over 2 is log 3 minus log 2. Log 2 is equal to 1. So minus 1 plus 1 is going to cancel. And these two are exactly the same. So what's the overall complexity of this algorithm? Neither one dominates. They're both the same. Well, you know what the master theorem is going to tell you to do in these situations? It's going to tell you, hey, forget about this sum. Why bother adding it together if this is going to be the same thing? Where did this come from? Here's the original equation. Where did that number come from? Came from there. Where did that number go? It's in the base here. It just disappeared, but it's supposed to be there. It's log base 2. If you knew that this was going to be the dominant factor, you could just say the complexity overall is n to the log this base of this number. That's what the master theorem does. It checks it all in advance, and it says, in this kind of situation, you can just look at these two numbers, and that's your big theta. And that's what happens here. And I'll give you the criterion and when you can do it, and we'll do a few examples quick, just by looking at the numbers. But right now, I want you to see the summation so you see the distinction. All right, questions?
So can we really ignore the 2n term?
Yeah, any power that's greater than 1, however small, is going
I
to be
mean,
greater than a constant.
you'd have to get an enormous n for it to be insignificant.
You're saying, can I ignore this 2 here?
Well,
Is that what
No,
you're saying?
he's saying the minus 1.
the minus 1.
Oh,
Because
absolutely.
Log 3 is so close to n, you'd have to
And-
get an enormous
and-
number of n.
But n is strictly small o n to the log 3. This is really bigger than this asymptotically.
Absolutely.
And I agree that you'd need big n's to see that happen. But theoretically, this is a worse algorithm. This is a worse algorithm than this. Linear is better than this.
Sure.
I should mention one thing, just because this is coming up now, before I go on to the n squared case and show you what happens. I want to say this because this gives you a big picture about algorithms and maybe the difficulty that theory sometimes has for catching up with practice. This is good theory, and it gives you a way of organizing algorithms into a hierarchy. But let me give you an example of an algorithm that's a real-life algorithm that has a particular complexity, and the complexity is worse than linear, but for all intents and purposes, in a real physical life universe, it will be completely linear, even though the theory says it's worse than linear. So that means the theory and the practice are kind of breaking down there, but it's still interesting. And I'll show you this in just in a couple seconds. This function takes a number and raises 2 to the power in a stack as many times as that number is. So for example, f of 1 means you have just one stack of 2's on top, so that's 4. F of 2 is going to be, good. F of 3 is going to be, no, 2 to the 16.
Why would f of 1 be 4 instead of 2?
Just the way I defined it, that the number of 2's in the stack. F of 3 is 2 to the 16, right? It means I got 2 and then 3 2's in a tower, to the 2 to the 2 to the 2. So 2 to the 16. So 64,000 something. 65,536. All right. Powers of 2 people. All right, f of 4. Yeah, I'll just get my recursive friends to help me. This number is a huge number. This number is bigger than the atoms in the universe, probably. It's a big number. Okay? You're not going to ever make a computer that has this much memory, even if you're Gateway, right? Pentium inside. But 2 to the 65,000 is a big number. So once you get to 4 or 5, this is just a huge function. Now here's the inverse of this function. It's called log star n. If I put in 65,000 into n here, this tells me 3. If I put in 2 to the 65,000 into n here, it tells me 4. This number, for all practical size inputs in the universe, or in any conceivable universe, is less than or equal to 4. It's just never bigger than that. I know conceivably it grows without bound. If you put in 2 to the gazillion, this number will sooner or later get as big as you want, but not in real life. In real life, it's 4 or less. There is an algorithm that uses a set data structure that I talked about briefly when we talked about sets, called a union find data structure. You construct sets, and the two things you're able to do with this data structure is, given an element, find the set that it's in, and given two sets, merge them together. It's a data structure that you could have as an assignment in Scheme. You could store it in lists if you wanted to. But the way this data structure is implemented is that it's very fast. And when you go ahead and solve the minimum spanning tree problem with this data structure, instead of the usual n log n time algorithm for minimum spanning tree, you get an n log star n algorithm for minimum spanning tree. So somebody writes this up, shows a good use of union find, gets a PhD, says I've improved the n log n to n log star n, good job. Did they come up with a linear time algorithm? No. This is theoretically worse than linear time. Practically speaking, we all know that this is 4n or less for anything in the universe. So practically speaking, it really is less than linear time. So this begs the question of what a better theory might be when you get into strange things like this. But it's something you should be aware of. There are weird functions that you really don't see the asymptotic stuff describing what really happens. And there's one example. Back to this problem again. We solved this and we said it was big theta n to the log 3. And now I want to know what happens. What happens when the function that glues it together, instead of being n, turns out to be n squared? I warned you I was going to do this in advance. Maybe some of you actually did it. I am getting a little tired of going through all the details of the algebra. You're probably getting tired of it too. So if you don't mind me short-circuiting this, I'll tell you what you get in that t of n step with the r times, and we'll compare it to what we got before. I get the same thing for the recursive part. That part doesn't change at all. The only part that changes is the gluing part. But here's my new sum for the gluing part. Instead of n on the outside, I get n squared. And on the inside, instead of 1 plus 3 halves, plus 3 halves squared, plus 3 halves cubed, all the way up to 3 halves to the r minus 1, what I get is 1 plus 3 fourths, plus 3 fourths squared, plus 3 fourths cubed, plus 3 fourths r to the minus 1. Now, without going ahead and solving this geometric series, which one of these terms is dominant?
The second.
This one is. It doesn't give two squats what this ends up being, as long as it's bigger than 1 or as long as it's a constant, as long as it's bigger than 0. This adds up to some number times n squared. This is less than n squared, right? It's 1 point something. So we don't care about this. It gets dominated by the gluing part. The master theorem keeps track of which part is going to be dominant, tells you in advance, and mentions, therefore, that in this case, where the gluing part is dominant, the complexity has nothing to do with these numbers, but is simply the same complexity as a single gluing stage, big theta n squared. OK, who has a question so far? So there's two possibilities. Either this part's dominant or this part's dominant. So far, we have those two possibilities. The third possibility was the first thing I did today. When I did 2n over 2, and I added n, what was the answer to this recurrence equation? It was big theta what? N log n. What happens there is that neither one really dominates. You kind of get the perfect balance of splitting and gluing. And what results from a perfect balance of splitting and gluing is this gluing function gets an extra factor of log n. OK. When you design a recursive algorithm and you know all these things in advance, you should know how much slack you have as far as how many subproblems you're going to divide. If you know what the complexity is going to turn out to be based on this number and this number, then you know if I divide it into two parts, how many different pieces I can have and still keep the algorithm under n squared. How much my gluing procedure is allowed to take before it ends up being so dominant that it doesn't make a difference how carefully I split the problems. Knowing this in advance helps you design algorithms, not just analyze them when you're done, but it helps you plan how you want them to be. It's really important. So that's what the master theorem is going to summarize, and I'm going to put it up on the board right now. And you got to be careful because there's a lot of conditions in this theorem. Let me be very specific now. I said that one of these is going to dominate, and the master theorem tells us which one. When everything's perfectly balanced, it turns out that the sum also dominates, the recursive part, but it doesn't dominate it equal to itself. It dominates it with an extra factor of log n. And in some sense, that's, I think, the ideal kind of balance.
You could find a case where both terms are equal.
You could, where one doesn't, you could. But in those cases, we know we just pick one of them. You could. They could be equal. It could time, yes.
What was your final answer on the current problem?
So this is big theta n squared, because that's dominating that. You don't like that?
I don't like it. It's 4 times, take the sum of the square brackets. It's 4 times 3/4 to the n minus 1. Or 3/4 to the r minus 1. 3/4 to the n minus 1.
Yeah. This is what I get exactly. Did I mess up?
I don't know.
I don't know either. I thought this just ended up being something smaller, but maybe I'm wrong. Let's check that in a second. Here's the master theorem. The master theorem takes care of recurrence equations that look like this. Some constant number of subproblems, some division of the size of each of those subproblems, some function for gluing the answers together. And it divides it into 3 categories. Category 1, 2, and 3. And the categories compare this function to some combination of these numbers a and b. And here's what it compares. Case 1. F of n equals big theta n log b a. If f of n and n log ba are the same, that's one case. The other 2 cases are when one's bigger and when one's smaller. We'll do an example in a second. Let me just write down the other cases. By bigger and smaller here, I mean asymptotically bigger and smaller. Three cases. Either they're the same asymptotically, or one's smaller or one's bigger. In this case, the overall complexity is n to the log BA times log n. That's like the first example I did today, where you get that extra log n factor. In this case, it's just plain, I should write big theta. In this case, it's just plain n to the log BA. That's like the second example I did. That's like the 3tn over 2 plus n example. And in the third case, I meant to do an example where the other one was dominant, namely f of n. Those are the three possibilities. This saves you all the boring work and summarizes it all in one nice result. Let's do some examples. Which one of these is bigger? N squared is bigger. Therefore, this should be n squared is bigger. Therefore, this should be big theta n squared. So the answer to your question is probably where I said take my word for it, you shouldn't have taken my word for it. I probably got that sum wrong, or I did something incorrect there. But it should have worked out to n squared, and I'm not sure what I did wrong.
That sum, I think, should have been 1 minus rather than in that case, because your geometric sequence factor was 3/4.
Mm-hmm.
Instead of, you had a term
yes.
minus 1,
Mm-hmm.
it should be 1 minus.
Oh.
And then the 1 multiply n squared would be the dominant.
Oh, yeah. That would have been more helpful. Yeah. Yeah, I understand what you're saying, Baruch. Right. Right. Baruch said I reversed the minus one. It should have been 1 minus. And you may very well be right. Whatever it was, the mistake was an algebra mistake. And I know that the kind of mistakes you all come to me and say, well, why'd you take off for that? Well, I make these mistakes, and I apologize. I should have been more careful writing the sum. Okay. Let's try each of these. We need to compare the functions to log of base this of this number. So let's try to do it. Hey, Joe, what do you know? Help me out. We're comparing n to the log of what? N to the log
Of 3,
base 3 of
9.
right. What's the log base 3 of 9? 3, 2, right. So 3, you shall count to 3. Neither shall you count to 4, except on... We're going to get that movie next time.
Good.
Log base 3 of 9 is 2. So that's n squared. So n squared's bigger. That means, which case are we talking about? Talking about case 2. This guy's bigger. That means that the order of this algorithm is n squared. Painless, right? Not only is it painless, but you should know when you're designing the algorithm. Oh, I've got this built in. You know, if it was 4 and 2, it would also be squared. Okay? Get used to, if these were equal, if it was 3 and 3, what would happen then? 3 and 3.
The same.
Log base 3 of 3.
So you'd average this.
So it's n. That means the two are the same. You don't average the two.
It gets the right answer.
The two are the same. No, you get n log n. Okay, if you had 3 problems of size 3 each with an n gluing factor, you get n log n as your result. If you have 9 problems, it ends up being n squared. What if you had 5 problems? 5 subproblems. It'd be log base 3 of 5. Is that bigger or smaller than n asymptotically? It's bigger. And what would the asymptotic complexity of your algorithm be? It'd be n to the 1 point God knows something. And that's why if you ever read in a textbook or in a paper, the complexity of this algorithm is n to the 1.732. And you're wondering, well, what kind of weird fractional loop gave this guy n to the 1.732? It comes from these kind of recurrence equations. Right? Not every complexity is just a loop in a loop, so that it's n or n squared or n cubed. You get it from here.
1.732
1.6. Something. All right. This one. What's the deal here? Can you use this?
The bottom is 5 over 3.
Yeah.
The bottom's 5 over 3, right? Think of it as, you have to write it as n over b.
Log of 5/3.
So if you write this as n over a number, it's n divided by 5/3. So it's the log of
1 to the base 5/3.
log of 1, log base 5/3 of 1. How do you get 1?
17-0.
Anything to the 0 is 1. So the fact that this is 3/5 is kind of just a red herring. Could be any fraction at all. Log base of anything to the 1 is 0. N to the 0 is a constant. This is a constant. They're the same. So the complexity of this algorithm is a constant times log n. This is big theta log n. This is big theta n squared. This is just as good as binary search. You don't have to divide something exactly in half and glue it together with one guess. That's what binary search is. You can divide it into something a little bigger than half. In fact, if this was 9/10 n, it would still be log n. As long as you're taking a constant fraction away, even if it's nowhere near half, you're still getting a log n complexity. This is the last one. Yeah. Yeah, because you have to write it as n divided by a number. You have to match that picture, Joe. So 3/5 n is the same as n divided by 5/3. Okay? That's a good question. I should have made that clear. So you have to get the number down there somehow. Although you should keep in mind that in this particular case, it wouldn't really matter either way, because any number to the 0 is 1. So you get constant and constant. What about here? What are we comparing here? Log base 4 of 3 to n log n. Log base 4 of 3 is what? Between 1 and 2, right? No, smaller than 1. Less than linear. And this is bigger than linear. So this is bigger. So the complexity of this algorithm is going to be n log n question. All right, so now I have to, why did I write question? Now I have to tell you what I really mean by these less than equal signs and greater signs. I kind of fudged one little thing. Less than and greater than, I kind of fudged it, and I said, well, asymptotically. And I let it go, and nobody needled me because it wasn't obviously wrong. But now we're getting up to this problem, and I want to tell you exactly what I mean and what the theorem says. The theorem says that if you're greater than or less here, it's got to be by some polynomial amount. It can't be just bigger by a log n factor. It's got to be bigger by an n to the something. Okay? Otherwise, the theorem won't work. The theorem only works when this greater or less than is by a polynomial factor. So let's go back and compare this one. Here we get n to the 1 point something, say 1.3, and we have n times log n. Is it okay to use our trick? Is it polynomially bigger? Oh, sorry, this isn't 1.3. This is 0.8 or something, right? So is this polynomially bigger? Yes or no? Well, it's certainly log n bigger, but it's also n to the 0.2 bigger, right? It's n to the something bigger. It's the difference between log base 4 of 3 and 1. So you do have that little bit extra that you can still grab onto. If this were exactly n, then you couldn't use the master theorem because they'd only have a log n extra factor. But we still have enough to get a polynomial improvement. Let me write it up here. N to the 0.8 versus n log n. This is n to the 0.2 times log n bigger. That's a polynomial, and that's okay.
Where's that 0.2 coming from?
The difference between 0.8 and 1. Okay, if it was just log n, you couldn't do it. So let me give you now an example that you can't use the master theorem for, and then I'll tell you what you do when you can't use it.
So if this was n and n log n, you couldn't use it?
Absolutely.
That would be the example.
Exactly. Good, Michael. Good. Do you have a question? You're thinking about something? No? Okay. Let me do one example where you can't use it. So everything we did so far is right, but you got to know what that means. There's also, by the way, there's another condition here that I'm not even going to tell you. Some particular condition about f of n. It's an obscure condition that you rigorously need to have be true for this theorem to work, but it's almost always true for any functions that you'll see. And I won't bother even telling you what it is, and it'll never come up. But you should realize that the real theorem has some peculiar condition on f of n, and that exists too. And I'm not even sure our book even goes into it. I know the Revest Algorithms book would tell you what the condition has to be on f of n, but I think our book just says assume f of n is some polynomial, because they're all the right functions. This is just n. This is n log n. This is a log n factor larger asymptotically, but that's not enough for us to use the theorem. It does not fit into big theta. It does not fit into less than or greater than polynomially. There are gaps in this theorem. This theorem does not divide every one of these recurrence equations into one of three categories. You can fit into one of these three, or you could be out in limbo. This is an example that's out in limbo. It's neither big theta of each other, nor is it a polynomial time greater. It's just log n greater. So this doesn't work. And what do? You got to go back to your substitution drawing board and actually go ahead and calculate it. Okay. In doing this, you get a really, really interesting sum, which comes up in a lot of other areas, and it's good technique. So I think it's worth actually doing this one and seeing what it gets. And when we're done doing it, I'm going to give you a theorem that actually works for when you're a log n factor bigger. And then you'll never have to do this sum again. But you should at least know that the master theorem doesn't cover this. All right, questions about it? Who recognizes this recurrence equation? Towers of Hanoi, right? Remember how we solved this? We did repeated substitution, and then we got a long geometric series, and that's when I first told you how to sum a geometric series. So here's how we're going to do it today. We're going to change variables. I'm going to create a new variable relative to the t's here, and I'm going to get a recurrence equation that's the simplest one you've ever seen, just like the compound interest one we did on the very first day. So here's my new change of variable. S of n, it's my new variable, equals t of n plus 1. How is this going to help? Let's go ahead and change this equation in terms of S of n.
S of n minus 1.
S of n minus 1, that's the same as t of n, right? Equals
2 times S of n minus 1 plus 3.
Here. I don't think so. T of n is S of n minus 1. So every place you see a T of n here, you put an S of n minus 1. So T of n minus 1 is 2 S of n
Minus 1 minus 2.
minus 2 minus 1 plus 1. There we go. Let me do it again, since if I flubbed with the chalk, you're going to think this is harder than it really is. We changed the variable. And if you're thinking, why the heck did he change the variable that way? And you're probably wondering why I haven't explained why. And I will in a minute, because this is a magic trick. I change this variable, I get t of n equal S of n minus 1. And every place I see t of n, I put an S of n minus 1. Except here, I messed it up a little, because here I have t
Minus 1. The inside, for example. S of n minus 1.
2 times
S of n minus 1. Minus 1.
S of n minus 1 minus 1. This is Tn minus 1 is Sn minus 1 minus 1. Sn minus 1 minus 1 is in place of Tn minus 1. And then I add 1 from that one. Now let's fiddle with this a little.
Sn minus 1 equals Sn minus 1. Hold on.
I'm putting that over there. This is what you get.
2 times Sn minus 1.
If you fiddle with this just a little bit, all the constants go away and you get the simplest recurrence equation you ever saw in your life. This is just like compound interest. This says that S of n is just twice of the one before it. What's the solution to this if I say S of 1 equals 1? By the way, what's T of 0? 0, right? What's S of 0? You can figure out your base case just by translating it through your change of variable. So if T of 0 is 0, then S of 0 is 0 plus 1. So S of 0 is 1. How do I solve this recurrence? The repeated substitution here doesn't even develop a sum. It's the easiest possible one. You just keep multiplying by 2 and by 2 and by 2 and by 2. So what's the final answer? S of n equals 2 to the n. So what's T of n? 2 to the n minus 1. All right, so what's easier, doing a geometric series or doing this? This is easier. But how did I know that this would be so pleasant? Well, the real way I knew is because I knew the answer is 2 to the n minus 1, right? And I know that 2 to the n comes from a simple recurrence equation. So I just go backwards, and I know the change of variables is going to work, and I run it through, and I make it look like magic. But Sam's right. I can do this backwards the first time because I knew what the ending was. I know the end of the story, so I make the story look good. But if you get good at this, you can start guessing in advance that the end is going to look in a certain way and changing the variables before you get into the crazy sum. And that takes ingenuity, and it takes practice, and it takes experience. So how do I expect you guys to do it if you're just beginners?
We will be mathematically mature by the end of the year.
Just take these pills. The kind of problem I expect you to do that's this style is I'll say, here's a ridiculously looking hard recurrence equation. Try this change of variable and see what happens. You'll see things like that. And then you'll learn to appreciate this technique without being in the position of, gee, how do I get it? Because it does take experience, and it really isn't so easy to guess the change of variable. But you should at least get the intuition here. This particular change of variable, what it's really doing is just kind of doing the geometric series in advance. The geometric series is double everything with that extra one term on the end. So let's just add the one term now so everything would just be double. That's kind of what's going on. So let's say this was plus 4. And you do the same exact change of variable. What do you end up getting? You get Sn minus 1 equals, you tell me, Joe, you thought of it. You're stuck now.
2 times S of n minus 1 minus 1 plus 4.
Right. So now let's try to solve for S of n. S of n equals 2s of n minus 1 minus 2 plus 4 plus 1. Is that it? Minus 2 plus 4 plus 1. 3. Yeah, Jesus. We're a little better.
So if you did repeated substitution, you substituted it back.
Good idea. You can do change of variables more than once, right? And if you notice, this gets you to something a little better. Maybe we could change the variable again and change the variable again. And then you might wonder, well, maybe we could do all these changes of variables all at once. Oh, good, good. You will be mature. Give me back the pills. We did change of variables. We did the master theorem. We did repeated substitution. We're not going to do linear algebra stuff today. We're not going to do linear homogeneous today. I still owe you that one sum for the one that didn't work for master theorem. Maybe I'll ask Tara to do it in recitation as a review. The good news is recitations from now for the next few days are going to be nothing new. They're going to be, let's do lots of these until everybody feels they can completely do it. All right, so they're going to be a lot more what recitations typically are. We don't have to catch up. We're right here. So bring in a problem. You don't know how to do it. Bring in a sum that's tough. You can talk about it. It'll be nice. I don't know how long that'll last, but at least for the next few days, we're set. This will be a 10, 15-minute topic, then we're done for today. What are you whispering, Michael? Okay. Let's have chalk flake races. That's what I got from my 6th graders. I got that guy, I got that guy. And they get real excited when their flake wins. Jeez. Guessing an answer to a recurrence equation and proving it by induction is a great example of the power of induction. It lets you use your intuition. You get used to recurrence equations after a while. You get a sense of, oh, I think I know what that one is, but I don't have the slightest idea of how to prove it. So I'm going to take a darn good guess, and maybe I can just verify my guess by induction. And you don't have to get the exact closed formula. All you have to do is guess a big theta and verify that by induction. And you get what you want with a lot less effort. And you can rely on your intuition. So it's cool. The example I'm going to do is an example that comes from algorithms, a real-life example. I'm going to put a recurrence equation up on the board, and I'll tell you the algorithm that it's from. We're going to look at it, scratch our head, say, God knows I don't want to do this with any techniques because we don't have any techniques that are going to work. We're going to guess an answer because I'm going to tell you what I think it should be, and then we're going to figure out how to prove it by induction. The big picture. We're going to try to prove it by induction. I know if I did it the right way the first time, you'd say, I think I get that. And then when you try to do it yourself, you'd say, I got what you did in class, but now that I try to do it myself, I can't do it. So I'm going to do it the way I think you would try to do it the first time, which is I'm going to do it wrong. Okay? I'm serious. I'm going to do it, and it's going to mess up. And right when it messes up, instead of having for you to come to me, you'll be here already. And then I'll fix it, and we'll do it right. And I think that way you'll learn it better. Okay, now it's not really wrong. It'll just be a bad guess the first time. And we'll improve our guess. So it'll be a good experience. A good experience. Here's an equation that comes out of an algorithm for finding the median of n elements. Don't ask about the details of the algorithm. It's quite a complicated algorithm. We'll spend a day on it or so in February, whenever we get there. But it's an algorithm that takes n elements and finds the middle guy. Now, you can always find the middle guy by sorting the list, right, and pulling out the middle guy. That takes n log n. So if you've got any idea of how to pull out the middle guy, it better be better than n log n, or I can just send it to my sorting man. This algorithm, therefore, we hope, is going to be linear time, proportional to the looking at every single element exactly once. It's not obvious how to do that. It's not clear at all how to do better than sorting, but you can. And it turns out, in the details of this algorithm, we solve a problem of 1/5 the size, we solve another problem 70% the size, and then we do 15 n steps to glue them together. Well, for one thing, we don't have just one set of subproblems, 3 subproblems n over 2. We have 2 different ones. For another thing, if we tried substituting, we get these long, ugly summations where 2 things would start developing. We just don't want to go in that route. It's just going to be ugly. So instead, we're just going to guess that this is linear time and try to prove it by induction. So our proof is going to be by induction on the size of the problem. We're going to assume that it's linear for smaller problems, for, say, things less than n, and we're going to try to show that it's actually linear for size n, using the inductive assumption, working our way up. And the only thing we know to help us, besides the inductive assumption that it's linear, is we know this. We know that t of n is no bigger, is less than or equal to tn over 5 plus t7n over 10 plus 15n. So I'm going to guess a wrong guess, just because I have no clue what this complexity is, and I'm going to guess that this t of n is less than or equal to 60 times n. And don't ask me why I picked 60, because I picked it for no good reason. I just picked it. I'm hoping that this is less than something linear times n, so I picked a number, 60n. And I'm going to try to prove this by induction. I'm going to try to prove that t of n is less than 60n, less than or equal to 60n by induction, assuming this is true. Everybody with me so far? it turns out that you can't do this. We're going to get stuck. But the point that we get stuck is a point that we can backtrack and use a better number and get it to work. Here's my base case. T of n is less than or equal to 5 as long as n is smaller than or equal to 6.
And this is part of the definition.
Yeah, this is part of the definition. This is the algorithm. If it's got less than 5 elements, can do it in. If it's got 6 or fewer elements, it can do it in 5 steps. Okay, you give me 6 or strictly less. 5 or fewer elements, I can do it in 5 steps. Something like that. That's the base case. All right, let's go ahead and try to do this. By induction, here's what I know. N over 5 is a smaller problem. Everyone agree than n? I'm trying to prove Tn is less than or equal to 60n. I'm going to assume by induction that Tn over 5 is therefore less than or equal to
60n.
60n divided by 5, right? Or 12n. By the same inductive assumption, T of 7n over 10 is smaller than or equal to 42n. Those two things I get for free by my inductive assumption. And now I'm going to go ahead and use the one thing I know for how to combine things and relate them to T of n to see if I get a conclusion. Hello, Donna.
Did we miss anything?
Oh, no. We're just lecturing backward today. We'll be finishing at 9. If I can spin my feet fast enough for the world to go around at the speed of light. This is smaller than 12n plus 42n plus 15n, and that equals 69n, and that's smaller than 60. Crap. Right? Crap. It would have worked perfectly if that 69 turned out to be smaller than 60, but 69 is bigger this week than 60, so it doesn't work. So we have to come up with a better constant. So one thing might happen this. We might end up not being able to find any constant. Maybe this isn't linear time. Maybe we guessed wrong. And you'll find that out after a few more tries. But rather than keep trying vaguely and randomly, let's do this whole trick again. And instead of using 60n, I'll just call it kn. And I'll just make the k whatever I need it to be at the very end to work, instead of guessing. So if I had started this whole thing and I'd say, okay, so let's let T of n less than or equal to kn, yeah, maybe you would get it, maybe you wouldn't, but I think this is clear. But now everything gets more complicated. My inductive assumption, Tn over 5 is less than what now? Kn over 5. The minute the specific example goes away and things get general, you lose it unless you have some kind of picture of the specific example in your head that you can graph the generality on. So here you go. 7kn over 10. And let's go through the same steps. So now let's figure out what this is. Let's add it together. Kn over 5 is the same as 2kn over 10. True? So I get 9kn over 10 plus 15n.
We can have an equal now. You don't have to have less than.
Yes, you're right.
But that has to be less than.
I'm hoping that this is less than or equal to kn. I'm hoping. If this is, so if I want this to be true, I've got complete control over k, right? I picked you. So I can pick him to be anything I want him to be. Or her. Oh, yeah. I don't know. I'm hungry, too. Let's move all the k-ons on one side.
Let's take all the ends out.
All right. All right, I don't usually let Sam tell me what to do, but today it's such a good idea. All right, take all the ends out. I agree. Take the ends out. Let's put the k's together. So I get how many k's on this side? K over 10. And here I get 15. So k's got to be bigger than or equal to 150. So if I had just picked 150 at the beginning and ran through the whole proof, and everything would have worked, and I'd say, see, therefore, T of n is less than or equal to 150 times n, and it's linear time. And you wouldn't have ever bothered asking me how I came up with that number 150 until 2 days later when you hit it on the problem set, and you'd say, well, how did you ever come up with that 150? So now you know, right? You don't really come up with it. You guess wrong. You figure out what the k has to be.